Okay guys, starting with a chapter called machines. Now we have seen that live example where I was trying to lift my bay. What's so easy? That was so simple. 55 kgs. And I tried to lift up a cylinder, which was very difficult. However, that's not machine. But in order to lift up a cylinder, we use some trolley. We use some sort of a support. And wasn't that simple, right? That's a machine. A machine is a substance, right? Which makes our work easy. It makes our work simple. That's it. So it is a help to the humans. That's what a machine is. So if I talk about getting down to brass tacks at once from the theoretical exam perspective. What are the uses of a machine? So we are out here with a chapter called machine. Okay, in uses of the machine, first, machine acts as a force multiplier. Second, it acts as a gain in speed. Third, change in direction. And fourth, it helps to apply the force at a particular point. So to apply the force at a particular point. So these are the four uses of a machine. Let's understand. Force multiplier. I can't lift this up. I can't lift up a car when there is a puncture. So what we do is we use a screw jack. With the help of a jack, right, the car gets lifted up. When the car gets lifted up, obviously it's a machine. It acts as a force multiplier. It multiplies the force and helps me to do my work easily. Second, gain in speed. Simple example. I have to go to my friend's place. Yeah, I'm taking a bicycle. Bicycle's a machine. That's it, simple. I reach faster than walking all the way to his home. Change in direction. I've gone to a village. Okay, I've gone to a village and I have been assigned a task. Lift up the water from a well using a bucket and a rope. So I have been given a rope, a bucket, and I have to push the bucket inside the water and then, oh gosh, lift up. That's heavy. So what I do is I use a pulley. A pulley. Okay, there is a rope tied to a pulley. I just have to pull it down. So can I say it is with gravity? Obviously, pulling up something is so difficult. Pulling with gravity is so easy. Change in direction. So pulley acts as a machine. Applying force at a particular point. Simple, stupid example. Take a door. In a door, can I say the handle is at the edge? So obviously, isn't that a particular point where I can just, with the help of my finger, I can just pull and push the door. So that particular point, that application of point is very essential, right? So it helps me. So that handle is also a machine. So machine need not be something like a G.I. Joe or something like a transformer or something like an engine. No. Anything, any instrument, any substance which makes my work easy is a machine. And these are the four uses of a machine. Right. My second answer is about the definitions from the board exam point of view. Right. So in definitions, the first definition we are going to talk about is load. All right. Let's see what is a load. Load is my resistive power. Can I say I want to lift up a gas cylinder which is almost 15 kgs. That's a load. So what I do is I can't do it. I'm a bit weak to lift up a cylinder, not my girl. Right. So if a gas cylinder is there, I will use a trolley where I will put the cylinder on the trolley and I will just push it with my leg. So that trolley is a machine. So can I say load is that gas cylinder. So can I say load is the resistive force? It is a resistive force which has to be overcome by that machine. So I am saying, hey machine, We need to lift that and make my work easy. So load is the resistive, oppositive force which needs to be overcome by the machine. Effort. Effort is the force. They both are forces. So obviously, load is measured in Newton and even effort is measured in Newton. These both are, guys, forces only. So they are different. Effort is a force applied on the machine to overcome the load. Come on, listen. I put that gas cylinder on that trolley, but I have to push the trolley, na? With my leg, didn't I push the trolley? So can I say my leg is the effort? Or if there is a button, a remote control, I have to operate the remote control, na? So can I say effort is a force which we put on the machine and tell, hey machine, come on bloody, lift up the load. You have to do something for me. That's why have I made you. Yeah, why am I using you? So can I say effort is the force applied on the machine to overcome the load? That's my aim. That's my objective. The third definition is about the work input. Now this is the way I'm going to write input. It's allowed. Input. Work. I am doing work. I am putting my effort on that machine. So work input is the work done by me. It is the work done by the effort on the machine to overcome the load. So what is work input? Work input is the work done by the effort on the machine to overcome the load. Fourth is the work output. Work OP, output. Work output is the work done on the load by the machine. Output, I want results. Now I gave my input, I'm done with my stuff. I want the output now. I want the results. Yeah, I don't want any excuses, please. So I can say work output is the work done on the load by the machine. Simple. All right. After this, my next definition, it's a flurry of definitions. Yeah. The third definition is about, I guess, the mechanical advantage. And much more about mechanical advantage. We call it as MA. Okay, mechanical advantage is equal to the ratio of load to effort. It is equal to the ratio of load to effort. Load is measured in Newton. Effort is measured in Newton. Newton upon Newton, cancel. So I can say it has no units because it is a ratio. So definition is mechanical advantage is equal to the ratio of load to effort. No units because it's a ratio. Now remember three cases. Case number one, load is greater than effort. Load is more, effort is less. Case number two, load is equal to effort. Case number three, load is less than the effort. So let's work on these three cases, guys. Let's begin the journey. First, understand. I want to lift up an elephant. Elephant. Dangerous. So can I say load is more? Effort is less. I don't have that much power or force to lift up an elephant. So can I say load is more? In my example, effort is less. So obviously, I am going to use some machine which is going to act as a force multiplier. Please, machine, I'm talking to a machine. Hey, machine, please help me to lift that elephant. So I want your support. I want force. I want more strength. That means I can say that if load is more than effort, we are going to use such a machine which acts like a force multiplier. And obviously, if load is more, effort is less, mechanical advantage is going to be greater than 1, and such a machine acts as a force multiplier. Second, mechanical advantage is equal to 1. This, when load is equal to effort. Load is 5 Newton, effort is 5 Newton. Cut. Answer is 1. So when they both are equal, I can say mechanical advantage is equal to 1. Such a machine acts as a change in direction. Simple. I went to the village. What I did was, there was a bucket, well, and a rope tied to the handle of a bucket. What I did was, there was a pulley out here. Let's draw it here. Let's draw it, guys. Okay. So we had a pulley. A rope out here and a rope tied to a bucket. And there was a well. So obviously, guys, can I say this is the effort and this is going to be the load. So what I'm doing is, if 5 Newton is the force, 5 Newton, I will have to pull with a force of 5 Newton. So the load and effort are equal. Where? Your load is equal to effort. They both are the same, right? All what changes is the direction. The load is going up. The transfer, it's going upwards and the effort is going downwards, right? So this is a change in direction. But the mechanical advantage is equal to 1. Load is less than effort. Look, load is not much. Effort is much more. For example, I give you a task which is not a Herculean task. It's a simple task. Cut your hair. Come on, you will say, sir, so simple. You take a scissor, cut it. Obviously. Now that was not a difficult task. But when you go to a barber shop, they do it very fast. They do it quick. Can I say we want speed? We want that speed. We don't want some force to help us in cutting the hair. We want speed. So in such a case, a scissor is an example of a gain in speed. So I can say in the third part, mechanical advantage is less than 1. Such a machine acts as a speed multiplier or a gain in speed. Now always remember, a machine simultaneously can never act as a force multiplier and a gain in speed. It can either be a FM, force multiplier, or it can be a speed multiplier. Alright, my next concept is about velocity ratio. VR. Okay, velocity ratio is equal to the ratio of distance covered by the effort to distance covered by the load. Distance of the effort, distance of the load. And also remember, it has no units because again, distance, it's a ratio, cut it, no units. Remember, velocity ratio is directly proportional to mechanical advantage. We're going to prove this. So very similarly, on a very similar note, if velocity ratio is greater than 1, it means machine acts as a force multiplier. Equal to 1, change in direction. Less than 1, gain in speed. Right, this was about the velocity ratio. The next concept is about the efficiency. That's how we represent efficiency, eta. Okay, some like this, yeah. Efficiency is equal to the work output upon work input. Or you can also call it as power output upon power input if the time is the same, because power is work upon time. So this can be written as a ratio of work output to work input. We're going to study about this much more, but first I want you to just go through these things and we're going to attack efficiency and a relationship between efficiency, velocity ratio and mechanical advantage. Okay, we're talking about the efficiency, right? Yeah. Efficiency is the ratio of, if I write simple work output and work input, it doesn't make that sense, yeah. Nope. Look, what do you mean by work output? Work output is the work done on the load by the machine. On the load. Output means the result which I get. Result means the load. Input is effort, output is load. Please connect it this way. Load is connected to output and input is connected to the word effort. Please. So I can say work output is the work done by the machine on the load to, it's a ratio, to the work input. Work input is the work done by me, the effort on the machine, right? And if I talk about efficiency percentage, this is going to be multiplied with 100. That's efficiency percent for you. Now there is a relationship. Listen to me. If I take this further, work is force into displacement. We've studied that in work chapter. Yeah, come on, second chapter. Don't give me that look, huh? Don't give me that look. Work is equal to force, I'll call it as F1, into displacement, S1. And F2, same formula. Even in the denominator, we have work. Work is Fs. Fine. Now, remember one thing. As I said, when we talk about output, we are talking about load. And when we talk about input, we are talking about effort. All right. So I can claim that this force, okay, that force is nothing but load, right? Load. And this force is nothing but effort. So force is load and effort. So F1 is nothing but load and F2 is nothing but effort. This S1, it is the distance covered by the load. Distance covered by the load is dl. And S2 is the displacement or distance covered by the effort, which is dE. Now remember, load upon effort. Few minutes back, we've done this. Come on, yeah. Load upon effort is nothing but mechanical advantage. Nice. And distance of effort to distance of load, it starts from the bottom. It starts from the denominator, the formula, guys. Distance of effort upon distance of load, I can say it is velocity ratio. So there you go, guys. MA upon VR into 100 is efficiency percent. Now, if you remove the percent, you cross multiply. Efficiency into velocity ratio is the mechanical advantage. Guys, I can claim that mechanical advantage is directly proportional to the velocity ratio. I told you around 5 to 6 minutes back that I'm going to prove the relation between efficiency, VR and MA, where I am going to say, okay, with an upthrust, the flow, the speech, that they both are directly proportional. So if VR increases, mechanical advantage also increases. Now one pointer, it's a note. Remember this, a note. Mechanical advantage changes. Velocity ratio never changes, it remains the same. Now what do you mean by that? Whenever a machine gets older means its a time period increases, yes, from where it was originated. There is friction in the moving parts of the machine. There is some wear and tear, yeah. There is some rigidness, that some rigidity decreases. The machine starts making noise, and this is all because the mechanical advantage decreases. So remember one thing very cautiously, that due to the friction of the moving parts, due to the rigidity, the change in the rigidity, the toughness, mechanical advantage decreases, but velocity ratio remains the same. So velocity ratio is unaffected by the moving parts of the machine. It does not change with time. Mechanical advantage decreases with time. Fine. After this, we have our next concept. It is about the ideal machine and the actual machine. Now what exactly is an ideal machine? An ideal machine, ideal. You want an ideal girl for yourself. And girls, you want ideal guys for yourself. Ideal should have all good qualities. Should not smoke, should not drink, should not look at the other girls, should be rich, should be kind, should be generous, should be good looks, should be, tall, dark, handsome, should be good to talk, should be a good human being, should have a good soul. Now, look at the list. Look at the bloody list. Come on, yeah. It's not possible. That's ideal, imaginary, imagination. Yeah, that's an ideal machine. So in an ideal machine, we say that output energy should be equal to input energy. That means how much energy you put in to a machine, the machine should give same amount of energy back. That means if I'm giving my 100%, I should get 100%. Is that possible? You write an exam. I know everything in an examination. I'm expecting 100 and 100. But teacher always has some sort of a problem with my paper. She will give me 99. No, tyrant, 1 mark out here will go because I didn't like your answer. Simple. So I can say that always the output energy will not always be equal to the input energy. There is some sort of energy, some amount of energy which is lost into the surroundings in the form of heat, radiation or something because of the friction, the moving parts of the machines and all, yeah, etc. So I will say that an ideal machine has 100% efficiency. But this is an imaginary condition. An actual machine, and also if it's 100% efficiency, this is 100%. 100% means 100 upon 100. 100 cut. What can I say? I can say that VR is equal to MA. So for an ideal machine where the efficiency is 100%, the input energy is equal to output energy, damn, mechanical advantage will be equal to the velocity ratio. This is for ideal. If I'm talking about an actual machine, the realistic approach is in life. Always remember, input energy, how much I give, is always going to be greater than how much I get. Is always going to be greater than output energy. That is, the work output is going to be less than the work input. And I can say efficiency percent is always going to be less than 100%. And mechanical advantage, okay, is always going to be less than the velocity ratio. So from here, I can always claim it's a give reason. Velocity ratio is always greater than or equal to the mechanical advantage. Velocity ratio can never ever be less than the mechanical advantage. We just saw either velocity ratio is greater or velocity ratio is equal, but that's also for an ideal machine. For an actual machine, VR will overrule. So remember this concept. After this, I talk about why in an actual machine, the efficiency is less than 100%. Why? We're going to talk about it in a while with a couple of more answers, and then we're going to start with the B part, levers. So let's see why is efficiency less than 100% for an actual machine. So I say that the efficiency is less than 100 because remember, when a machine works, it is operated for a longer period of time. Yes? What happens to the moving parts of the machine? The moving parts of the machine are not perfectly rigid. Okay, they are not perfectly elastic and frictionless. The string is not elastic. So I can say that because of all these factors, there is a loss in energy. And when there is a loss in energy, guys, the efficiency is going to be less than 100%. Yeah, because there is going to be some friction. There's going to be wear and tear. As the machine keeps on running, moving, there has to be the bruising of the parts of the machine, as a result of which the efficiency is going to decrease, guys. So in this chapter of machine, till now, we spoke about many things. All right. We spoke about the uses of the machine, the definition. What is efficiency? What is load, effort, mechanical advantage, velocity ratio, the relationship between them, certain give reasons, ideal, actual machines. All right. This was my A part of the machine chapter with you. After this, we're going to go with the B part, okay, which is called levers. But just go through the A part thoroughly.